So, hi everyone. Good morning or good evening, depending on wherever you are right now. So, it's my great honor to say a few words about our today's speaker. So, today's speaker is Belal Ahmed. He is a current graduate student at University of Illinois Urbana-Champaign. He completed his bachelor at BUET in 2015. And after that, he joined for our power generation company for 2 years around. And after that, he moved into USA, completed his master's from University of Miami. I guess today's talk, he is going to talk about his master's work. And right now, he is looking into low-dimensional material physics, especially for thermoelectric materials. So I hope today's talk is going to be very interesting, and we will have the question opportunity for the audience after our talk. So with that, thank you, Belal, for attending our talk today, and it's all yours. So if you can start presenting your slides. Thank you.
Thank you very much. Yeah, thank you very much for your generous introduction. So let me just go into the presentation mode. So let's get started. So good morning, everyone from this part of the world. As Shotudis introduced, I'm Belal Ahmed. So I'm a graduate student at the University of Illinois, Urbana-Champaign. So today I'm basically talking about the molecular dynamics study of the self-healing polymers. So let's get started. So before getting started, actually, I like to say some disclaimer about it and also some acknowledge a couple of my colleagues and professors here. So as Shotudit mentioned, actually, this study was actually part of my master's dissertation at the Miami University, which I started at the fall of 2017. So I like to acknowledge my professor, Mehdi Janjani, and Professor Justin E., which I was co-advised at the Miami University. Also, I would like to thank my collaborator, Professor of Chemistry, Professor Dominic Konkolevich, and two of my colleagues, Bori and Netmi. So if you see any experimental plot in this presentation, so these are actually from the experimental guys, like Professor Dominic Konkolevich group. So I haven't done any experiment, but I collaborated with them. I basically did the whole computations in this project. And also, I don't like to miss the opportunity to thank our sponsor, NSF, and the SESPRF. And last but not the least, I would like to thank the Miami University and also the Ohio Supercomputing Center for allowing me to using their supercomputing resources. So that was a nice experience when I just moved from my laptop to the supercomputing. So that was a wonderful memory. So let's get started. So as the title said, actually, I'm going to talk about the self-healing polymers. So in the first place, actually, I would like to talk about what is self-healing itself. So the definition of a self-healing material is called a material with the ability to heal itself autonomically. Is called self-healing materials. So actually, there are a lot of self-healing material around us, actually. It's a very prevalent phenomenon in the biological world, like from the plants, trees, even the humans. If you look at the human beings, like from our blood clotting to the repair of the fractured bones, all these are actually involves the self-healing process. So actually, the biological nature actually perfected it over the million years course of evolutions. But now we scientists and engineers are trying to just figuring out actually how to actually do the self-healing process in the artificial, like in our engineering materials. If we can do that, it could wholly revolutionize our design spectrum. So I have just actually, for example, put an example here for you guys to just appreciate it. Actually, this figure is showing the latex coagulation in a tree. Just I like to get my laser pointer so that you guys look at it. So it shows the latex coagulation in a tree. If you look, this tree is uninjured, and after some time it got injured. Then you see the sequential time snapshot of how it is getting actually self-healed. Like after 18 minutes, it healed itself. So now the scientists are taking inspiration from this phenomena in the biological world. So now, what could be the potential application of the self-healing materials? The first thing that comes to my mind, actually, there could be a lot of applications. But the first one, I think, like you can think of like interplanetary missions, like where actually NASA's Curiosity or the Perseverance rover is now roaming in the foreign terrain in the Mars. Now, if if this vehicle actually got damaged, like its wheel or any other part of it actually got damaged, actually it's very hard to repair. Like you need to send another missions or you need to abandon the mission. So in this case, consider like actually if you can build some part of the vehicles, maybe it's wheel, maybe some part, if you can build it using the self-healing materials, if it somehow get actually damaged when running in this foreign terrain, actually if it can heal by itself, that would be the best solution. So that could save a lot of money. So that's one wonderful could be a wonderful applications. You can see we always actually familiar with the flat tires in the summer, especially. So in this case, it's actually if your tire is made of like self-healing materials, it could actually save a lot of money. And other applications could be like the polymer-based composite. As always, the polymer have the potential to revolutionize the composite field, and also it could be in the organic electronics. And last but not the least, actually, the polymers have inherently very low thermal conductivity. So if you can somehow engineer its electrical conductivity, so it has the potential to be in the thermoelectric field as well. And there could be a lot of other applications, you name it. So let's move forward. Now, approaches to the self-healing. So there are a couple of approaches in the self-healing in the literature. So one approach is called the capsule-based approach and the vascular network-based approach. These two approaches, I like to describe them together because they are pretty similar. So in the capsule-based or the vascular network-based approach, actually, you have small microcapsule or the tubular networks inside the material matrix. So in this capsule or the vascular network, so there is kind of healing agents. So when a crack appears in the materials, maybe some capsule or the vascular network gets ruptured, and the healing agent comes out, and they do some kind of polymerizations or some kind of reactions, and it helps to heals the material. But looking at the pictures, the capsule-based and the vascular network-based approach, you can surely say that it's very complicated to design. Actually, its design is not that simple, and also it cannot sustain like a large number of cycles. Like if it healed once, and if the same crack appear in the same spot or some other spot, actually it will not be able to heal, because those capsule or the vascular network that ruptured, they won't be able to get it back. So its number of cycles it can operate, it's very limited. And lastly, another approach, this is called the intrinsic approach. So this intrinsic approach can be done by the reversible reactions or the hydrogen bonding or the ionomeric coupling or the molecular diffusion. So let's talk about it, because in my project, actually, we have used this intrinsic based self-healing approach. So in our case, actually, mainly you see those atoms, they are capable of dynamic bonding. Like they can associate and the disassociate. They can again associate and the disassociate based on the thermal fluctuations, based on external stimuli from the environment. So there is no restriction like the capsule or the vascular network in this kind of materials. They have inherently the dynamic bonds, which can help them to heal by itself. So as you mentioned, as there is no actually capsule or the vascular network, it can be healed for a large number of cycles. But the disadvantage is that there can be chance of deformation of the material over the time. So let's actually now put all our concentration in this intrinsic self-healing approach as we have implemented it in our materials. Okay, let's move forward. So the objective of this study was actually basically to modeling the self-healing behavior and also modeling the mechanical properties and modeling the thermal properties of these materials. So the method that we have used in our study is basically a combination of experiments and the simulations. So for the experiments, actually, we have done some rheology tests, like some tension tests, this kind of stuff. And for the computational stuff, we basically use the molecular dynamics simulation. So I have used the coarse-grained classical molecular dynamics simulations, which I'm going to talk soon. So now let's talk about a little bit about the coarse-graining and our model for the polymers. So actually, if you look at the polymers, actually, they are very complicated. You can easily say that they are not something like the periodic structures where every atom sits in a periodic lattice and they have well-defined structure throughout the whole simulation spectrum. Because the polymers is like kind of fluid that flows, and their behavior is certainly very different from the behavior of regular periodic solids. So if you look at the atomistic models of the polymers, they are very complicated, and you have a one monomer and then another monomer, they link together. So in a monomer, it's a molecules where you have a lot of other molecules associated with it, a lot of atoms associated with it, and they have internal degrees of freedom. They are actually, now you see that actually it is very complicated to model the polymers atomistically if you don't like to miss any details. But it is computationally very expensive, and also it takes a lot of time to simulate those. So what we did actually, we made simple model out of this atomistic model. So like you take one monomer and you replace it by one ball. You take another monomer, replace it by another ball. So we take one monomer and lump it together and say this is one bit. So this one ball, you see this big ball representing one monomer, we call this big ball as bits. So now you see that the two ball is connected by a spring. So we call this model a bead spring model. So in a one bead spring model, like in a simple polymer chains, you have beads connected by the springs. So now let me tell you that this bead represents one monomer, and this spring represents the covalent bond in between them. And we know that this is a harmonic spring; they can stretch. Excuse me. They can actually stretch infinitely, and they represent the covalent bond between the two monomers. So this is just a normal polymer chains. Now let's get back to our case. So in our case, actually, now get back to the crosslinkers. So in a simple chains, we have crosslinkers in the two directions. So in our material, our experimental colleague that are studying our material, the material we are modeling, actually, they have two types of crosslinker. One is called a covalent crosslinker, and the other one is called a non-covalent crosslinker. Usually there is a simple cartoon of the polymers. So the covalent crosslinkers, I like to mention that as you are thinking, as the name implies, they are actually connected by the covalent bonds. And we know that the covalent bonds is very strong, and they're very inert as well. Like a normal temperature fluctuation cannot do anything to that bond, and they're very hard to break. You need to input a lot of energy to break this bond. So these bonds are kind of static in nature. They don't break here. I mean, you need a lot of energy to break those bonds. On the other hand, if you look at the non-covalent crosslinkers, so these are actually non-bonded interaction. We have modeled this using the non-bonded interaction. By non-bonded interaction, I mean actually the LJ interaction. So this non-covalent bond actually represents in our material is kind of hydrogen bonds. So it's kind of hydrogen bonds. So these hydrogen bonds are actually susceptible to temperature fluctuation. Like a temperature fluctuation can cause them to dissociate, again form, again dissociate, again form. So they are actually very dynamic in nature. So at room temperature, maybe a lot of things happening inside the material. Those bonds are forming and dissociating, forming and dissociating. So it's give a dynamic nature to the material, which actually is very helpful for the self-healing. So after saying that, I like to talk a little bit about our polymer network. So based on these crosslinkers, we have two types of polymer network. So this is very important. So please pay a little careful attention to these two building blocks. So one is called a single network. This is called the SN building block or the SN polymer. And another material is called the IPN or the interpenetrating building blocks. So let's first talk about the single network building blocks. So in a single network building block, you have a one polymer chain. And in these polymer chains, you have both type of crosslinkers. So you have the non-covalent crosslinker and the covalent crosslinkers. But on the other hand, in the IPN building block, you have one polymer chain. In this polymer chain, you have only covalent type of crosslinkers. You have another polymer chains. In this polymer chains, you have only non-covalent type of crosslinkers. So there is no mixing actually in a single polymer chain. So just remember that. So now, if we make this network, so in a single network, if we look another polymer chain, so when these two polymer chains crosslink together, so they will be bonded by both covalent crosslinker and also non-covalent crosslinkers. But remember that covalent crosslinker bond with covalent crosslinkers, and non-covalent crosslinker bond with non-covalent crosslinker. So covalent crosslinkers cannot bond with the non-covalent crosslinker. That's the rule. So if you look at the interpenetrating networks, so as we have two types of polymer chain where we have two types of crosslinkers, so one network will be entirely bonded by entirely bonded by the covalent crosslinkers, as you see. So these two polymer chains. On the other hand, another type of polymer chains, other polymer chains will be connected by the non-covalent crosslinker. So this one. So there will be two network actually, one wholly connected by the covalent crosslinkers, another network wholly connected by the non-covalent crosslinkers, and they are penetrating into each other. And we are calling it the interpenetrating network. So this is actually very important because based on these network architectures, so their mechanical and the thermal properties actually differ, so which is really important, which is studied in this presentation. So that's very interesting. So after making those polymer chains, we randomized our simulations, like we randomized this whole thing so that actually there is proper mixing of those polymer networks, and actually, so when you ensure that our mixture is homogeneous and isotropic, we just compressed our system. We compressed it to the desired density. Like in our case, it was like very low density, like the density of water, very soft and soft rubbery like material. So when you got this desired density, then we perform our testing, like the tension test or thermal conductivity measurements. So we perform this on these specimens. So let's move forward. And also, I'd like to mention, if you during the time of talk, if you have some questions, actually, you can pause me if you want actually to ask something. I won't mind. So let's get started. Move forward. So first, I would like to actually talk about the self-healing. So in the self-healing, actually, let's see how our experimental colleagues do the self-healing. So they have this kind of dog bone shaped specimen they make out of these polymer materials. What they do actually, so if you see, this is a dog bone shaped specimen. They cut the material in half, and then they press the material, press the two parts together with some compressive force, and they hold there for some time. After some time, actually, they see that their specimen actually gets healed. Their specimen gets healed. So then they perform the tension test on the specimens and see that how the material recovered its properties and compare it with the uncut one. So there is an example of actually how the material behaves after the tension test. Like this is the site where it was originally cut, but when they performed the tension test, they found that actually it breaks from another locations. So it suggests something that materials heal itself because it's not breaking from the original locations where it was cut, but it would break actually. So actually the spot where the material starts breaking, it's stochastic. So every time they did a simulation, they found that actually it actually breaks from different locations. So which suggests really something interesting going on. So in our case, actually, the way we simulated the self-healing in our study is that actually we made two polymer parts, and first we actually place invisible wall in between them. So then actually we define two rigid bodies, and we apply the compressive forces on our systems. Then we actually remove the wall and allow the polymer to actually heal itself and allow some time. Then we find when the polymer was actually healed, depending on how much time you allow, then we apply from the tension test to see that actually how much it recovered. So in order to simulate this cut, we have just actually replaced it with wall and compressed it in our case in order to imitate the experiments. Okay. So now let's look at some of our experimental results, what our colleagues found. So when they perform the testing, so we will study the two parameters is actually important. One is actually the healing time, how much time you allow for the system to heal itself. And another one is actually the application of the compressive force, how much compressive force you apply, the magnitude. So in the case, we see that actually from this plot, this is the uncut case where your material is not being cut. This is the very pristine structure, pristine materials. In other cases, this actually shows that how much time we actually allow the material to heal itself. It is very intuitive that actually when you allow more time, like 30 seconds, then 60 seconds and 120 seconds, we see that actually the materials recovers better. It means that actually when you're allowing more time, it is healing better. And that is very expected because you need some time for the material to heal itself. Now for the compressive forces, some people may think that the compressive forces may damage the material if you go beyond some limit. That's of course true, but we found that within actually certain limits. So we found that actually when we applied more compressive forces, we found that the material actually heals better in terms of its peak stress, and also the strain values is doing better when you apply the forces. So both of them have some positive effect on the positive effect. I would like to answer this question now. Would you like to get the answer? Like one guy asked me, how did you implement the invisible wall in the methodology? Sure.
So
like
we have a question and answer session. I think we can go in details into that session.
Yeah, sure. Actually, if you guys have any questions, just put it in the chat list. So if you don't forget that, so I will get back to each questions when our presentation is over. I think it will be good. Okay, that's a good question. Okay, let's get started. I'll get back to you guys after the presentation. So yeah, let's move forward. Yeah. So then we actually try to simulate what we get out of our simulations. So we have found the similar trend actually, but we found that actually when we actually increased our healing time in this case, actually we found that actually in terms of peak stress, it recovers better. Although the behavior may be a little different from what we are seeing in the experiment, because we are using the coarse-grained simulation. So we are missing a lot of atomistic details. So it's no wonder that actually we are getting the trend right, but actually it's no wonder that we don't even expect that our result would exactly match with the experiments, because that's actually that's you have to sacrifice, because we are doing a coarse-grained simulations and we are ignoring a lot of atomistic stuff. But it's good that actually the peak stress is increasing with the healing time, so that means the material is healing better. And also for the if you look at the force, we see that when we apply the more forces, like from 3 nanonewton to 300 nanonewton to 12 micronewton, we see that actually the material is behaving better. It's recovering its properties well with the time. So why that is happening? Because our experimental colleague cannot see the atomistic details, but we can see the atomistic details, and we can actually understand the origin of the self-healing behavior atomistically, which we would like to actually explore in the next couple of slides. So when we actually looked into the behavior, like bond formations between the crosslinkers, we found that actually we found that this bond formation between the different crosslinkers during the self-healing time, actually it increases very rapidly at the beginning, and when the time goes on, it's flattened out, because I think because those pairs actually find each other. In some cases, they are not actually capable of finding each other. So originally the rate is very high, because there are a lot of crosslinkers available to find each other when they actually crosslink with each other. So the other pairs may remain actually not being able to find their pair. So they remain uncrosslinked. So in this case, it shows that actually those bond formation increases exponentially, and then it gets flattened out. So now it actually, in our case, actually the main resistance actually during the tension test is mainly coming out of this crosslinker. So when you have large number of the bonds, that's for sure that you have actually more resistance. I mean, the properties will be better. So like in our case, you can think of now, in the case like when the self-healing time is very low at something 0.0174 nanosecond, like you are very close to the origin. So in this case, you have low number of bonds. So you have low peak stress, and you are allowing more time for the materials. Actually, you are having large number of the crossing bonds. So you have better properties. So it explains that actually how the materials recover with the time, but it doesn't say anything about how the materials recover with the application of the compressive forces. So another interesting thing that actually it cannot be recovered fully in mechanical properties by just increasing the healing time, because it gets flattened. So you need to come up with some other method to accelerate the self-healing process, which would actually increase the number of bond formations. So let's move forward. So now we'd like to see actually atomistically what happens when we what happens when we apply the compressive stresses. So when you apply the compressive stresses just before the simulations, you see there is an accumulation of compressive stresses in the materials. That's very expected. When the self-healing does, if you look at this contour plot, you see those compressive stresses disappear, and we can see the same thing is happening. Actually, same thing is happening here. You see the pi atom stress before the self-healing, You see there's accumulation of negative stresses here. There are a lot of negative stresses. When the self-healing is down, so those negative stresses disappear. So when we apply the compressive stresses in the material, we actually are accumulating strain energy in the material. And we see that when the self-healing is done, we see that those strain energy is disappearing. So now the question is where those energy is going, because energy cannot be destroyed. It needs to actually convert into some other form of energy. So that could be interesting. That could lead us to actually some interesting fact. So where does this energy is going? That's a big question. So let's move. So when we actually found the effect of bond formation, effect of force on the bond formations, and we have found that actually, so this when you apply the more forces, it accelerates the bond formation process. If you look at this two plot, that's clearly show that when you apply the more forces, the bond formation process is accelerating. Okay, now we can actually anticipate that actually this bond formation process is actually helping this compressive forces is actually helping the material to do better. So in terms of bond formations, so now we can actually say that. So the compressive the strain energy that disappeared in our previous cases is now helping the material to form more bonds. So actually the strain energy is now being converted into the chemical energy of this inside this bonds. So that is actually helping the material to recover better. So now we can actually think in terms of Arrhenius picture, like in the classical Arrhenius picture that we are studied in our first year chemistry courses. We know that for a reaction to happen, so there is a potential energy barrier. So energy barrier, when you apply the force, you are actually reducing this energy barrier, so reducing this activation energy, which makes life a little easier for the crosslinkers to come together and bond with it. So this reduction, this compressive forces is actually changing the energy landscape and allowing the bonds formation to be easier. So if you see this rate of forward reactions from the Arrhenius type equations, you see that actually depends on the delta E, which is the activation energy barrier, which is a function of the compressive force. So it can be, this energy barrier can be engineered using the application of the compressive force, which in terms is actually helping the reactions to be faster and actually accelerate the self-healing process, and also helping the material to recover its properties so well. So that is actually the end of our self-healing study. So now let's get back to our modeling the mechanical properties. So when we study the mechanical properties, first we try to actually replicate some of the results that our experimental colleague is finding. So they studied the effect of cross-linking density. So in the effect of cross-linking density, they found that when they increase the cross-linking density, they found that material is behaving like brittle material. So you see that the low cross-linking density, it is kind of rubbery because you don't have that kind of resistance, because it just flows. It just flows when you do a rheology test for the polymers, because there is not that much cross-linking. But when you increase the cross-linking density, it gives the material more rigidity, and it acts like a kind of it fails like a brittle material. All its peak stress increases and the strain value decreases at which it fails. And when we actually did the same simulation, in our case, actually we have found a similar trait. That means when you increase the cross-linking density, we found that our peak stress value increases, and also materials behave some failure becomes some kind of more brittle-like. So that does mean that our model is working, because we're getting the similar trend. It is able to capturing the physics that's happening inside the material. So that's a good sign. So let's move forward. So now the big questions, as I mentioned previously, of the IPN and the SN polymers. So in the IPN and SN polymers, so when our colleagues actually did the rheology test for the SN and the IPN polymer, they found always that the IPN polymers outperform the SN polymer in terms of mechanical properties. So they were wondering why this is happening, why the IPN polymer is better than the SN polymer. They don't know the reason, because they don't have the access to see what's happening inside the materials atomistically. So we try to answer these questions using molecular dynamics simulations. So let's see what we have got out of MD simulations. So this is actually our tension test specimens, like as a normal tension test. That way you do it in the molecular dynamics simulation. You define a fixed region, you have a stretching region, you define a moving part, and you apply the strain rate or tension, and you allow the material to stretch, and you record the stress and strain. And you see that actually in our case also as well, we also found that in our case that the IPN actually outperforms the SN. We have the same kind of range. Don't bother about the shape of the curve because it's very length and size dependent, and also actually we are using the coarse-grained simulations. But in our case, we found that actually it's at the same train for the different strain rate. We see that actually, but the IPN is outperforming SN. So that's a good sign. That means that our model is actually good. It is able to capturing what's happening inside, at least. I mean, in terms of trend-wise, it's okay. So that's not bad. So now we try to answer the questions why the IPN outperforms the SN. So as I mentioned previously, those two network structures actually, so the difference actually comes from the cross-linking. So in one case, we have just only one type of crosslinker in one chain, but in other case, we have the both type of, in the SN case, we have the both type of crosslinker in one chain. So then we looked into the bond energy, non-covalent bond crosslinker bond energy and the covalent crosslinker bond energy when you apply the strain. So we see that actually for the case of the non-covalent crosslinker bond energy, we found that actually, so for the IPN case, the energy is always higher than the SN case. If you see here, but the total covalent bond energy remains quite similar when you apply the strain in the material. So that does mean that it is the non-covalent crosslinker which is doing something which is giving some extra advantage to the IPN materials. I like to mention that the cross-linking density for the both SN and the IPN polymer is same in those two materials. Okay, so there is no difference in terms of cross-linking density. They have the same number of crosslinker in the both materials, but we see that the total covalent bond energy for the IPN and SN case, they are similar, but the non-covalent bond energy is always higher in the IPN in comparison to the SN, although they have that same cross-linking density. So now the question is, so what's happening here in this case? What happens to the non-covalent bonds here? So as the non-covalent bond energy is higher in the IPN in comparison to the SN, we can say that actually, so higher bond energy means actually there is more crosslinking possible between the non-covalent crosslinkers in the IPN materials in comparison to the SN. So as they have the more non-covalent bond formations, it allows the more non-covalent bond formation in the IPNs, which is giving it extra advantage. So what happens when you have more non-covalent bonds? But why is IPN is having more non-covalent bonds? We agree that the more non-covalent bond in the IPN is giving it some advantage over the SN. But why? Why the more bond formation happens in the IPN? So the reason why more non-covalent bond formation happens in the IPN is that consider two polymer chains. In the SN case, you have both type of crosslinkers. So in one polymer chain, it has both covalent crosslinkers and the non-covalent crosslinkers. As I mentioned previously, the covalent crosslinker are very inert. They are very hard to break. So when the two polymer gets crosslinked, one polymer chain gets crosslinked with the other polymer chains in case of SN. So this non-covalent bond actually, so this covalent bond actually dictates, it actually restricts the polymer, because when it gets covalently bonded with some other chains, it reduces the degrees of freedom for the polymer chains, like rotational degrees of freedom and the translational degrees of freedom for the polymer chains. It kind of fixes and reduces the other degrees of freedoms, which actually discourages the non-covalent bonds to form with the other polymer chains, because they need to actually get in touch of, need to come in contact with a certain radius with the other non-covalent crosslinkers to come in contact. But if the covalent crosslinker actually reduces their degrees of freedom, it's actually creating an unfavorable situation for the non-covalent crosslinker to crosslink with the other non-covalent crosslinker. That's why the number of non-covalent bonds is decreasing in the SN network. But in case of IPN, in one polymer chains you have only covalent crosslinkers. In another polymer chains you have only non-covalent crosslinkers. So this restriction is not there for the IPN. So which is actually creates a more favorable situations for the non-covalent crosslinkers to crosslinks and crosslinks. And these non-covalent crosslinkers is what is actually contributing for the better mechanical properties of this IPN in comparison to the SN. So that's what is happening actually. So if I say thus the non-covalent crosslinker will be geometrically bound and less free to move in the SN materials, which is not there in the IPN materials. As a result, actually, it produces more non-covalent bonds, which in turn gives better mechanical properties. Okay. So that was actually the end of our mechanical properties study. Then we did some actually the thermal properties study using the molecular dynamics for our case. So let's look at a couple of our studies for the thermal case. So for the thermal case, actually, it's not an ideal playground like using the coarse-grained molecular dynamics simulations for the heat transport, because you lose a lot of degrees of freedom. So in this case, it won't be really good because your thermal conductivity will not match with the experiments. Even actually, we didn't get even try to do some experiments on the thermal transfer measurement, but we are able to get some trend right actually for our case. So we use the non-equilibrium molecular dynamics simulation. So in the simulation, as you are maybe familiar with this kind of stuff. So we define heat source and the heat sinks. And when our system equilibrates, we get our temperature distributions, which is a straight line you see from the heat source to the heat sinks. Then when you plot this temperature distribution, you get the slope by fitting a line in this, you get the slope. And also you measure the heat flux from your MD calculations. And after that, you can actually calculate your thermal conductivity from there. So it is the method. You guys may be familiar with it. So now let's move forward. So in our case, actually, what we found actually, we compared the three cases, like a single chain, just a single chain. Then we actually tried our for the IPN polymer and the SN polymer. For the three cases, you see the temperature distribution. So if I extract the thermal conductivity, we see that actually these are actually normalized in terms of a single chain. You see that the single chain has 2 order magnitude of higher thermal conductivity than the IPN and the SN. And the IPN has almost actually 3 times higher thermal conductivity than the SN materials. So single chain has higher thermal conductivity. That is very expected because you have a single chain. So when you think about the heat transport, we think in terms of phonon actually. So in a single chain, when a phonon propagates, it is less scattered because it doesn't have any crosslinkers or any other stuff. So the phonon can propagate actually easily in those materials because there is no aperiodicity in this one single chain. So that's why we have a larger thermal conductivity, almost 2 order of magnitude than the IPN and SN. For the IPN case, actually, as you remember, these are actually it allows more bond formations in the IPN. So when you have more bond formations, the approximate way to think about is that actually when you have more bonds in the IPN, so that means the more route for the heat to transport. So as a result, I think the thermal conductivity increases. For the SN case, actually, there is less bond formation, and also the structure is more irregular in comparison to the SN. And that's why it actually leads to more phonon scattering, which reduces the thermal conductivity. So then we try to actually find some way, how can we increase the thermal conductivity of these polymeric materials? Because for some applications, we need some quick heat removal from the for polymer-based composite or some other applications, we want polymer to be, in some cases, very conductive. So how can we actually tune the thermal conductivity? So one way to tune the thermal conductivity is to actually apply the strain in the material. So as I mentioned, in a single chain, we found that the thermal conductivity is 2 order of magnitude higher than the other cases. So that does mean that actually it's something related to the straightness of the polymer chain. If you, in our case, like when you compress our system, we know that our polymer chain is very curled up. It curled up in space. So when the phonon propagates in those polymer chains, actually they get scattered from here and there. So it reduces the heat transport. So if we can actually strain the material and allow the polymer chains a chance to be somehow straightened, it would help actually to improve the thermal properties. So you see that we apply the strain in the material and we recorded the thermal conductivity. We found that actually when we apply the strain, we found that actually thermal conductivity increases actually by some degree. So which is a good sign. That means that the hypothesis is working. So then we proved that it is related to the straightness of the polymer chains. We actually introduced a property actually. So it is there in the literature. So it's called the orientational order parameters. So it is actually a matter of how straight your polymer chain is. So you calculate this parameter with the strain. We found that actually it's increasing with the strain. So that means that your polymer chain is getting straighter as you are straining the materials. That is very expected. And this orientational order parameter can have value between 0 to 1. So 0 means actually your polymer chain is very curled up, and one means that your polymer chain is very straight. And it is, of course, averaged over all the polymer chains. So all the polymer chains we have here in this material. So it says that with the strain, the straightness is increasing, and this straightness is actually helping the material to have better thermal conductivities. So this is probably the last study we did on the thermal properties. So here actually you see that actually we did the effect of cross-linking density on the thermal conductivity. So when we increase the cross-linking density, we found that slight positive trend with the cross-linking density. We found that actually it is increasing with the cross-linking density. So the reason why, but even at the higher cross-linking densities, is getting saturated at even at higher cross-linking density, it will reduce actually eventually. The reason for that is actually the more cross-link means actually the more bonds. So the more bonds provides more routes for the thermal transport. So that's why actually at the beginning, when you increase the cross-linking density, it actually increases. But when we have actually, you have too many bonds, like when you increase the thermal conductivity to a very large degree, so it creates actually a aperiodic behavior, which actually increases the phonon scattering. Like when a phonon propagates, so it soon gets scattered by another phonons because of the aperiodic nature of the polymer. So when you have more bonds and more routes for the heat to transport, too many actually routes exist. Actually, it reduces the heat transport at a very high cross-linking density. Then we study the effect of temperature, how the temperature affects the thermal transport. So at the low temperature regime, we found that actually it increases with the temperatures. At the very high temperature, it gets saturated, and even at very high temperature, it starts to decrease. So when you think about actually the thermal transport, the thermal conductivity is proportional to the specific heat capacity and the square of the phonon group velocity. And also this is called the relaxation time of the phonon. So the relaxation time of the phonon is like when you think in terms of molecules, when the molecules like in the kinetic theory of the gases, this is actually the time between two successive collisions. So in our case, actually for the phonon, it is the time between two successive scattering events. So higher those this relaxation time, that means that your phonon can actually travel more distance without being scattered. So that also actually increases the thermal conductivity if you have higher relaxation time. So we know that the specific heat is actually proportional to the temperature, and the relaxation time is inversely proportional to the temperature, because when you increase the temperature to a very high degree, it reduces the time between two successive collisions or two successive scattering events. And I like to mention that this relaxation time, actually, the 1 over relaxation time is called the scattering rates for the phonon. So this scattering rates comes from the disorder and the enharmonicity. So in our case, our polymer is perfect. So it actually have no disorder. So this term is actually vanishes. So the main rate comes from the enharmonic contribution. The enharmonicity is that when you increase the temperatures, at the ideal situation, like at the ideal phonon pictures, the atom vibrates at the bottom of the potential well to and fro. But when you increase the temperature, actually, its energy level gets shifted. It shifted from the bottom of the potential well to higher. So now the potential well is no more symmetric, so it's more asymmetric. That's what is actually related to the enharmonicity. I mean, the potential well is no more harmonic, no more parabolic. So there is some parabolic nature, which is actually, dictates the properties. So at low temperature, actually, this tau remain constant. Therefore, the K increases because at low, we know that the C lambda increases with the temperatures. So it is unaffected at low temperature. This is all remain. It doesn't change that much at the low temperatures, or just less influence. So the thermal conductivity increases mainly due to the increase in the C lambda. But at the high temperatures, actually, we know that the scattering rate is inversely proportional to the temperature. So the the relaxation time goes down at the higher temperatures. So which is actually overcompensate the C lambda. So as a result, at the higher temperature, this K lambda start to decrease at the elevated temperature for a specific phonon mode. So if you sum over all the phonon modes, so it gives a negative trend. So that's the very qualitative explanation for results that we have found from the MD simulations. So that's the end of our thermal conductivity study. So if I just conclude, so we are able to model the cell fillings using the molecular dynamics simulations. We have found the same trend that our experimental colleagues found, and also we explained using the atomistic details what is So what is leading to the self-healing process? And also we were able to answer the questions like why the IPN outperforms the essence, and also our qualitative explanation for the thermal conductivity matches with what we found in the literatures, and it gives the hints that the IPN polymers is better in terms of superior in terms of thermal properties as well for the SN, as we know that the IPN is better in terms of mechanical properties than the SN. We have also found the evidence that it is thermally even superior, but we haven't done the atomistic case for the thermal conductivity. That would be one interesting things to look at in the future. So that is actually these are my references. So that's the end of my talk. Actually, thank you very much for your patience, and I would like to answer your questions if you have any. Thank you very much.
Thank you, Belal, for your nice presentation. Now, I would like to ask the audience to put questions. So there are two ways you can put question. One is you can put into the chat. Another is you can raise your hand and I can unmute yourself so that you can ask question. So there are a couple of questions already there into the chat box. So I would like to go
I'd like to check the chat box and actually to give the answer to this question. So the first question from the chat box is that, how did you implement the invisible wall in your methodology? Any particular MD command? Okay, let's get back there. So in the invisible wall, actually, you can actually set a repulsive wall. So what I did actually, so you can, so there is a couple of command actually, which uses the LZ, repulsive LZ potential. In the wall, it's called, you just search the wall command in the LAMPS website. You just actually search that wall command. So in the wall command, you can actually specify the location of the wall, and also you can actually use the LJ parameters actually to set it repulsive. Like you just search wall command, and you can actually then you can set the repulsive forces using your like LJ command properties. I did it for a long time, so you can actually set your equilibrium distance, all of the interaction parameters, so that actually it repulses the other atomic species. So you need to define that actually it repulses the other atomic species. So, and also you can actually define actually how small your region would be, repulsive region would be. So that's actually set up by the wall commands using the LAMPS website. You just search repulsive wall or the wall command in LAMPS, and you need to set up your parameters actually nicely so that actually you have a nice repulsive walls, and also you need to specify how thin your wall would be. So you just search it, the wall command. I hope that explains. If you have further inquiries, you can always actually contact with me. If you need to know, just search it and you find it, and you need to do some basic search. So after that, there is another question.
One thing. So for the next question, I think Anapalbi has a couple of questions. So I would like to ask him to unmute himself and ask those questions.
Yeah, sure. That's great.
So Anapalbi, if you can kindly unmute yourself and ask question. I think we have a couple of questions here.
Yeah, sure.
The first question I have is where both covalent and non-covalent crosslinkers modeled using the same potential like LJ, or only in case of the non-covalent linker LJ was used and covalent interactions were modeled using some other potential?
Okay, yeah. So that's a good question. So I like to go back to like let's go back to where we have seen those bonds. So yeah, so I like to mention here the covalent bond is not actually modeled using the LJ. So it's actually, you can actually define bond in the LAMPS, right? So you can actually define spin between the two bits, right? So this is not a LJ interaction here. So let me just get the pointer option. Okay, yeah. So the covalent bond, the covalent crosslinker is not LJ. So it's actually our user-defined bond. So you can actually define bonds between two atomic species using some spin, and also specify the spin constant. So there is called the Fene potential in the LAMPS. You must have heard about it, the Fene bonds. So you can actually use that for modeling this kind of covalent bond, and you can specify when it will fails, and also can specify the stiffness of those bonds. So this is not LJ. And this is the non-covalent crosslinker is actually modeled by the LJ interactions. That is the non-bonded interaction. So you can set up the particle type, and between two particle type, you can actually set up the interaction parameters to be attractive. When they come within certain range, it will be attractive, and they will form non-bonded interactions. So that's how the non-covalent the bonding is described in our model. So I think that's answer your first questions.
Yes, thanks. The second question is how were the IPN and SN modeled, the structure? How was it?
Okay.
Modeled?
Yeah,
how was
yeah.
it coded to be like?
Okay. So for the SN case, let's describe it first. So for the SN case, you have one polymer chain, right? So in this polymer chain, you have both the non-covalent crosslinkers and you have both the covalent crosslinkers, right? So you have these single chains and you repeat these chains. You make multiple chain out of this. Okay. So you make multiple chain out of this, and then you make a very ordered structure like that in this. Then you allow the molecular dynamic simulation to run. Okay. So when you allow the molecular dynamic simulation to run, so these crosslinkers actually, like here, they will be crosslinked with the other chain. So I have seen a very simplified case, like it just gets crosslinked with another SN chain, but there are a lot of hundreds, thousands of chain in our simulation. So they will actually like crosslink randomly or very randomly with the other polymer chains in this case. For the IPN, you have two type of polymer chains. In one type of polymer chains, you have only covalent crosslinker. In another type, you have the only non-covalent crosslinkers. And you actually repeat those two type of polymer chain in your system. You make a lot of copy of stems and actually set them in a simulation box, then allow your simulation to run, and then the crosslinks, the way it is defined. Like as I mentioned previously, this non-covalent crosslinkers will crosslink with the covalent one, and this non-covalent crosslinker will covalent with the non-covalent crosslinker. So that's the rule action. As I mentioned previously, it is defined by some kind of spin bonds, and it is the non-covalent, non-bonded LJ interaction. So you leave this interaction to happen in your simulations, and it actually gets crosslinks randomly, as you mentioned, like when you randomize your system. Does that answer your question?
So actually the volume is primarily filled randomly with the chains, and then equilibrated, and they kind of spontaneously cross links.
Yeah, exactly. That's right. Yeah. So you fill the volume, you fill your simulation box with this two type of polymer chains, and then you start your random simulation. You randomize. You allow those. You run the static dynamic simulations and allow the crosslinker to crosslink with each other in a random fashions. Like here, the way it is shown. Once you allow the sufficient time for the polymers for the crosslinkers to get crosslinking for the both cases, like you allow some time. So even in this case, some crosslinker may remain uncrosslinked. So that's actually a good questions. Actually, we could actually see that what percentage of the crosslinkers are crosslinked and what percentage of them are not crosslinks. So that's a good questions. What percentage of them is crosslinked? But we allow sufficient time and the temperatures to get crosslinks. When we are actually satisfied with that, looking into the structure, it seems they're crosslinks. Then we start compressing the systems. Like you compress the shape of your simulation box, because you need to attain the desired density. Like in our case, it is the density of the water, like 1000 kg per meter cube. So we compressed our simulation box or the volume fractions until we reached our desired volume fractions. When you reach our desired volume fractions, you stop compressing. So that is our sample. Then you just equilibrate your samples, relax your samples, and then you perform the tension test or other kind of property like thermal measurements or the tension measurement to determine the properties. Does that answer your question?
Yes, thanks. The third question is, how was the density of the polymer in the simulation cell kept realistic? In other words, how was the packing done?
The packing is done. Yeah, okay. So I just told that the packing is done is just by compressing your simulation box, right? So you know is how much polymer is there. I mean, how many polymer chain is there? You know their mass. You know their actually you know their mass and you know the shape of your shape and size of your simulation box, and you start compressing it, then you know actually and at what volumes actually you will reach the desired density. So it is just a simple calculations how much you need to reduce the XYZ dimensions in order to reach that volume fractions. So that's how actually by compressing the box we actually reach the desired density.
Thanks. The last question is actually the bond creation and breaking, was it done using any other fixes, or is it actually programmed inside the Fene potential you mentioned?
Oh, it can be done. So you need to actually, like this covalent crosslinker bond formation. So it is done actually, I mean, even before the starting of the simulations, okay? Like we define between which type of crosslinker, there will be a new type of bond, okay? So new type of bond, this, where you can actually define different type of particle types. So, so we define the different particle types. When you start the simulation, we said that if these two type of particle actually, which is responsible for the covalent crosslinking, if they come within certain distance, then the lens will actually decide that there will be a there will be a Fene bond between them. So you can actually, I think as I remember, actually we did it some kind of fixes, like maybe you can just search the Fene bond in lens. Probably there is a fix associated with it. I have used that. So it's been almost 2.5 years. So my knowledge may be a little bit rusty. So you can just search the Fene bond in lamps. I guess we actually define a different particle type, and in the simulations, when this two particle type comes within a certain distance, we define the new bond, which is done maybe done by a fix, I guess. Yeah.
Thank you so much.
No problem. Yeah, these are really good questions.
Yeah, I think there are lots of details he was asking. So
yeah.
Let's move to the next question from Anshuraj. So he's asking, to create the cross-linking polymers, what software did you use, and what should we bear in mind as we write the code?
Okay, so in our case, actually, it was a handwritten code, of course. So we haven't actually used any software to do that. So we have written our code. So it was a MATLAB code to generate this polymer chains, and also to randomly place these crosslinkers on the polymer chains, and you need to define the particle types and the bonds. So we have done using our own code. So we haven't used any software in the first place. I don't know actually whether any kind of software exists for that. So that's I think answer your first part of the questions. And the second part, what should you keep in mind when you do those kind of things? So actually, that's actually a very, to give it a very specific answer is really difficult, but I would say actually, so it depends on your model, which kind of modeling you are done. If you do the atomistic modeling, I think your situation will be very different from what I've done here. Other than that, if you do the coarse-grained modeling, also you need to actually you need to, of course, use the bead spin model in that case. So you need to define your particle types, and also you need to define the harmonic bonds in between the particles. So you can use the harmonic bonds from the lamps between the two beads, and also you need to define the two type of the crosslinker type, which could be done by some other atomic species. You could define the separate particle type for the different crosslinkers, and then normally the crosslinker interactions, you need to define the as the interaction between them. So as I mentioned, I modeled the covalent bond using the Fene potential. So you can use the Fene potentials similarly, and also like you need to attain the desired density, which I've done by compressing. You can use that also. You can, if you come up with some other ideas, you can do that as well. Yeah, that's it actually. I mean, the basic thing will be very similar. You need to use this bead spin model. So I think this harmonic bonds remain same for your case as well. But you can maybe come up with some better ideas about the covalent and the non-covalent crosslinkers. I mean, it's all of your choice actually.
So I think there is no more question from the audience. So let me ask one or two questions that
sure.
I'm curious about. So from the experiment of self-healing, I see there are two important aspects. One is the time scale of that experiment. They did experiment in terms of second, right?
Yep,
Whereas
yep.
we know in MD we cannot go beyond nanosecond. And
Yes.
another is the length scale effect, which is
Mhm.
they are doing bulk scale sample, whereas you are doing nanoscale sample.
Yeah.
So what you see the difference between these two? I know these results differs a lot, but
Yeah.
what would be the physical insight that can be transferable from this nanoscale to bulk scale science?
Okay, so that's really a very good question, actually. So the effect of the time and length scale is, of course, I think one thing is that actually, so like when you actually go back, if you think in terms of actually the implication from the length scale, for the length scale, actually, I would say actually normally the materials in the bulk scale have a lot of defect, actually. So in comparison, in our case, like in the only models, so there is no defect in our case. But in the real ones, there could be, I mean, defect. Maybe the crosslinkers missing. Maybe you have other kind of defects. So which would actually, of course, depreciate your mechanical properties and thermal properties as well, which we don't have here. So I guess actually to make it even more realistic in the simulations, I think it would be really hard because you need to actually insert some defects and other kind of things to simulate the bulk scale behavior. So other than that, actually, I don't see that. Other than that, of course, I would suggest that we are missing a lot of atomistic details, like in our case, because we are using the coarse-grained simulations. Mm-hmm. So that could also actually lead us the difference between the bulk scale effect and the nanoscale effect. So that actually comes from the modeling part, like how do you model your polymers? For the time scale, I would say actually for the time scale, like the properties that are really depends on very larger time scales, like if you want to model the creeping behaviors, that's actually material deforms over a very long time scale. Maybe the result would be different for the creeping behavior in those cases in our simulation cases in comparison to the experimental results. I guess that could be two issues, like the defects and large. I mean, when you have very slow time dependent deformations. So in our case, actually, we're probably missing those.
I see. And another question would be when you have your own CGMT model. So have you generated your own force field or are you taking from some literatures?
Yeah, so in our case, actually, it's pretty simple. So like we are not actually using, as I mentioned previously, any atomistic simulations. So we are using coarse-grained simulations. So only there is two type of interactions. So one is the bonded interaction, which we have modeled with the harmonic spring from the lens. And another one is actually the non-bonded interaction, which is the LJ interactions, right? So so both of them is actually there in the literature or it's available. So we don't need to actually find any other because we didn't use that atomistic case. Mm-hmm. So it's very simple, actually. Yeah, very simple. Like I would like to actually expand a little bit on your questions. This is really very good questions, actually. It's like if you see our results, our experimental results and our simulation results, you see there is a lot of difference. So there is a lot of difference. We don't even actually so we are just looking at the trends, right? So we are not expecting too much from this model because this is a very simplified polymer model. And also you see that the stress strain curve is not even smooth because this roughness is coming from when you stretch the system, those covalent and the non-covalent bonds are breaking, right? So when you have those breaking of the covalent and the non-covalent bond, you see the certain jump in your stress strain curve. And also in some cases, the results may be very unphysical because you cannot actually ignore the unphysical effects in your simulations as well because the model is very, very simplified. So we're just actually intended to just keep the trend right. So that's our success, I would say, actually. So it's more or less actually it was able to capture the trend and explain some feature of it. I think the atomistic study will be really interesting to see that how those. So in this case, like you need to actually use the reactive force field in order to model those dynamic and those covalent bond, I think. So that would be really interesting study to see that is when you scale it even down. That would be really interesting to see that how what we get out of this. Yeah, that's a very good question.
So Yeah, in this slide, I can see your strain is 20. So is that 20% or are you going up to 20 times?
20 times actually. So you
20
see,
times.
it's very large. You see, so
Yes,
these are
so
very
that's
rubbery type materials. You can stretch it long. And
yeah.
also I mentioned actually, if you see that the strain is something like 20 here, but if you look at the experimental results, it's 3.5.
Yeah, 3.5. Yes, and
Yeah.
also I was looking into the stress value. So it seems like your experiment is giving higher properties compared to your simulation. So basically your experiments, the bulk sample has the defect. Your nanos, I mean the MD samples don't have the defect, but it's still, yeah, I know.
It's
I mean
still getting
it's
the lower value. It's still
yeah,
getting the lower value. So
yes.
the result I think would be like tuning the parameter, algae parameters, and tuning the covalent parameter, which we are not actually interested because we don't like to actually match the values with the. You can match it with the like experimental results, but the first place.
Yeah, there is always this discussion. Yeah.
The simplified model you're using actually, if you submit to any journal, the reviewer gonna bash you.
Yes.
How do you get these good results with this the kind of very simplified model? So that's
Yes,
a very big question.
So probably sometimes this question arises like, how do you validate with experiment or this kind of thing? I think we should ask the question in other ways. So can you do nanoscale experiment? So that may answer some of our questions. So probably that is one way to go. So I see one more comment from Rishad. So he actually said this is a very nice talk. So
thank you very much for your compliments. Thank you very much. Yeah.
So if there is no more question or any other thing, then I would like to stop my recording.